Hey guys, welcome back. So this is a third video, and apparently this tool I have only acts up when I'm using my recording software. So apologies for that. So glad I wasted money on it. So here we're going to look at hemo. Dang it. I think I would have remembered this by now. Okay, we're going to look at hemocytoblasts. If you break down the word itself, hemo is discussing blood. Cyto is for cell, and then blast is for growth and development phases. So hematopoietic stem cells, HSCs, are the more common term. That's what I learned when I was in school. And there's going to be two types of these stem cells. Okay. We've got our myeloid ones that come from the bone, and some will become our red blood cells, like we talked about, while others will become our white blood cells, like we talked about. The others are going to be lymphatic or lymphoid stem cells, and they will grow up and become lymphocytes. And when we get to immunity, you'll see T lymphocytes and you'll see B lymphocytes. So, but when you're looking at them under a microscope on a slide, you cannot differentiate these two without further staining techniques. So just a heads up on that. All right, so hematologist is a word I was struggling for earlier. People who study blood, we've identified different stages. And if you're looking at the best figure to look at for this one is going to be in the book. It's on page 677, and it is figure 19.10. So when you guys are looking at that figure, if you know that, so the abbreviation EPO, there goes that stupid tool thing again. They're talking about erythropoietin, which is a hormone, and that's not supposed to be pointing to anything. But know that. And then when you see the abbreviation G, it's going to be for granulocyte, right? If it's followed by an M, it's going to be monocyte. And then the CSF isn't cerebral spinal fluid. It's colony stimulating factor or clonal stimulating factor, depending on your books vary. So, but this is going to be granulocytes, monocytes, clonal stimulating factor. All right. So I don't want you guys to freak out about the proerythrocyte. But I would like you guys to know that these two right here require EPO. Okay. The reticulocyte one itself actually is past the EPO requirement, so it doesn't actually need that hormone. But this is actually, yeah, let me fix this, guys. Hold on. Come on. Erase this. All right, so EPO is specifically for this guy. Fix that. All right, so erythroblast is past that. It doesn't need that hormone present. It's already used it. But as it gets down here into mature red blood cell, remember, when it goes between these two stages, it's going to spit out the nucleus, right? And start to form hemoglobin molecules before it actually becomes a mature red blood cell. So please keep that in mind as we move along. All right, so here's the hormone I was talking about. EPO is the abbreviation, and it stimulates red blood cells to grow. We do secrete it with our kidneys and our liver, specifically when tissues that may be in your peripheral, like your fingers, your toes, your arms, your legs, is low, and that would be called hypoxia. Hopefully you guys have already heard that, but if not, it just means low oxygen. So blood doping I don't really want to talk about too much in here. Your book does a pretty good job about it. So athletes have been busted doing this, and it's not only dangerous because of the way that they do it, but there's a whole litany of reasons that this isn't safe. And something that your book does not mention is that if you really, really want to increase the number of red blood cells, I'm so sorry about this, guys. I cannot believe this tool broke. It came broke. If you want to increase the number of red blood cells that you're actually producing, just become a regular blood donor, right? I cannot believe this thing. This is garbage. All right. So if you donate blood on a regular basis, I think it's every 10 to 12 weeks, this will increase the red blood cells. But athletes, whatever. Don't have anything positive to say about that. So the book talks about them reinfusing red blood cells that they've already stored. But athletes are using other people's hormones and packed blood, and that's the danger of blood doping. And after this video, we're going to talk about blood types themselves, and you'll understand a little bit more why it's dangerous. Okay, so erythropoiesis, or making red blood cells, you have to have amino acids present. You have to have iron present. You need folic acid, which is a vitamin. And then I don't know why they put folic acid separate from B12 and B6 vitamins, but you do need these. And we're going to get into we're going to do a chapter on nutrition, so don't forget about that. Pernicious anemia is from a lack of B12, and it can be treated with if B12 supplements, oral supplements fail, then you can do injections. So anyways, all right, hemoglobin is recycled to an extent that it can be, right? There are macrophages. Remember, macrophages developed from monocytes, right? And they're going to be present in the spleen, the liver, as well as the red bone marrow in your hip bones and your femur. They will engulf or phagocytize. See if I can read this word out without the pen breaking. Can apparently not. Phagocytosis or phagocytosis. They will engulf and eat them. When they do that, when the macrophages do that, they'll remove the hemoglobin molecules. If the red blood cells have been ruptured, and they'll take the components of the hemoglobin and they'll reuse them. This is way to recycle iron. So they're going to literally put this iron off and reuse it. So that can be done. All right, hold on. A couple other things we'll talk about just briefly. If you wake up and you have a patient who has red or brown urine, that means that they're having really abnormally high breakdown of red blood cells in the bloodstream. Hematuria, this one is where the entire whole red blood cells are actually found in the urine. And this can be from damage to kidney or blood vessels. So, anyways, if you've ever been punched in the kidney, they can lead to this. Your kidney will heal, but you may end up with some funny looking urine for a while. All right. So, again, with the recycling, we're going to pull this iron off, and it's usually Fe3 plus. We're going to remove it. And then if you want to remember that biliverdin is green, verde is green in a Latin language. And then when we get it to bilirubin, which we'll see with hemolytic disease of the newborn, it is a yellow-orange color. We also see this with when the liver starts to shut down. So, I'm sorry, my brain shut off. So we see this with liver damage or hardening of the liver, where it's not functioning properly, and it ends up, we call it, the skin ends up skin ends up looking yellow. And I'm not sure why this word is escaping me right now. But you can actually not just see it in the skin, but you can see it in the whites of people's eyes, where it should be white. Oh my goodness. Why can't I not? Jaundice. Oh, geez. Thank goodness. It's actually right here. Go me. Okay. So, but jaundice, we'll see it in hemolytic disease of the newborn. We'll see it in patients that have damaged livers, which would be, still can't remember that word. Hepatitis. Not hepatitis A, B, C, even though you can see it being a C, but inflammation of the liver. You'll see this yellow buildup, the bilirubin in the skin and the whites of the eyes. And we use intestinal bacteria that are normally present, as well as oxygen to get it converted from bilirubin to urobilins and stercobilins. All right. Once we pull it off the heme, like we mentioned, it's bound and stored in the phagocytic cell, which is what I was trying to write out, and it just got all ugly. And then it can also be released into the bloodstream. If it comes into the bloodstream, we're going to use an enzyme called transferrin. I would prefer if it had been named transferrinase. So you guys all knew it was an enzyme, but you'll have to just remember transferrin. Oh my gosh, transferrin is an enzyme. All right, so there. Okay, so come on, seriously. All right. And again, it'll get into the bloodstream. When the red blood cells are developing in the bone marrow, they'll absorb the iron and transferrins to help them synthesize the hemoglobin and get it to the mature erythrocytes. Well, I'm sorry, before it goes from erythroblast to the reticulocyte. So if you have a whole bunch of transferrins, they'll be removed by your liver and your spleen. These guys play so many roles in our body, but they'll store it as ferritin. And we're probably not going to talk about that much, but hemosiderin. So you're going to see a similar mechanism when you take micro. Take that. All right. So this is an interesting little figure for the book. So you have a red blood cell. It's gotten to the end of its life, 120 days. 90% of them are going to come into a phagocytic cell, a macrophage, right? That cell is going to say, hey, give me your heme group, rip off. Oh, I put FE3 in the last slide. I apologize. 2 slides ago. This should be my little guy. There he is. This should be a 2. I apologize. And then the FE2 will go back into the bloodstream, right? The rest of the hemoglobin becomes biliverdin, the green one, and then bilirubin, the yellow one. Any bilirubin bound to albumin in your bloodstream, we're going to see in the next slide that it's going to, not this slide, sorry, this slide, that it's going to go into your liver, okay? Come back a little bit. All right, when it's not broken down by phagocytosis, so the other 10%, these guys will get taken in if they got ruptured during the process of going through your body in the bloodstream. And that it's not atypical, but hemolysis is what it's called, or some people like to call it hemolysis. I just say hemolysis, like potato, whatever. Right. And then they'll eliminate those alpha and beta chains that I was talking about earlier in the urine. And those, if you've got your red blood cell, I'm forgetting this thing. You've got an alpha and a beta and a beta. These, when they get taken off, they'll be eliminated in your urine, so through your kidneys. Right. So I feel like this is a little bit out of sorts, but we talked about the ferritin coming out and being transported back to the bloodstream by transferrin, that enzyme I mentioned, right, and being put into the reticulocyte, which is this bad boy here, before it can become a newly released red blood cell. So the body likes to recycle things, right? And then again, it'll live for about 120 days. And as things get ruptured, they'll be pulled out, phagocytized, and we're going to reuse the alpha. No, we're not going to reuse them. We're going to dispose of the alpha and beta. We will reuse the iron. All right. So here you got your bilirubin, the yellow colored one, coming in through your liver, and it's going to be excreted with the bile. So they're showing your gallbladder right there. Oh, that's ugly, but whatever. So it's going to be excreted in the bile. Again, bilirubin is the yellow one. Then we add in any urobilins or stercobilins that we can pull out and put back in the bloodstream. We will. The rest will be eliminated. I'll get to that in a second. But again, if hemoglobin isn't phagocytized, we're going to eliminate these alpha and beta chains through urine, which will be the next slide. Here we go. All right, so anything not phagocytized and broken down gets eliminated. It goes through your kidneys. Hemoglobin goes through your kidneys and then eliminated out. This is one of your ureters, and it'll go down to your bladder, not shown. And then the bilirubin and whatever's not used for the urobilins or stercobilins, these guys will be eliminated in feces. So they're showing you the large intestinal movement. Why is this not working? Okay. So I'm going to pick up the next video here. This one seems kind of short, but this is the blood typing is going to be interesting. Well, I hope it's interesting. All right. See you guys in the next video.